Hello everyone, my name is IJAZ and I'm a PhD student in Computer Science department, and my topic for this mini project is effect of water and wind on forest fire intensity. So actually, a very idealized forest fire can be represented using a cellular automata. A simple cellular automata forest fire model consists of grid of cells where each cell can be in one of these three states: blank, occupied by a tree, or burning fire. So here at each step, the state of each cell on the grid is determined by four rules that the model carries out simultaneously, and here are our four rules. The first one is a burning cell becomes an empty cell. The second one is a cell with the tree becomes a burning cell if at least one of its neighbor is burning cell. The third rule is a cell with a tree ignites at probability F even if no neighbor is burning. The fourth rule here we have is an empty cell becomes a tree at probability P. Actually, fire modeling is not that simple. There are many complications because fire models must also capture information about weather, fuel type. Fuel can be anything that can burn, and topography, which greatly influence fire growth. Additionally, fire creates their own weather, altering humidity and other aspects of their surrounding environment. So this poses a formidable challenge for fire modelers. So for our experiments, we choose wind and from weather, and from topography we choose like water as a barrier. So here are our three research questions which we want to answer. First one is, how does tree density affect the fire spread? Like if we change the density to 0.1, 0.2, etc. And another one is, does weather condition, for example wind, affect the spread of fire? Third one is there any effect on the spread of fire due to barriers, for example water? So in the experiment we simulated the original forest fire model which I showed in the first or second slide with those four rules, and later on we included wind and water to see if they can influence the fire spread or no. And for parameters we have forest fraction, and P is like the probability of new tree growth per empty cell. F is like lightning strike, like if lightning happen it also can burn a tree. In the forest grid we took is 100 by 100, and this cellular automata is deterministic because we initialize the value by our own. It's not randomly initialized actually. So here are the simulation results of our this is the first experiment I did without including wind and water effect in there. So if you can see the first picture, the first video shows some effect of different parameters on fire spread. The first one is forest fraction, we put it as 0.2, and the tree growth to 0.05, and lightning effect is 0.001. And the second one we change the parameters. If you can see there are like some changes in the parameter values, and the fire spread is spreading differently. The third one also we actually reduced the forest fraction, like the tree fraction in the whole forest, and the tree growth is also increased, but the lightning effect is kept same, but the fire is like burning crazily. It's like a crazy effect I can see here. Here actually we modified the model and by adding water bodies. So some simple modifications to the code can add other features to the model that influence fire spread. Like for example, to add water bodies which can block the spread, I first defined a new cell state water and expanded the color list bounds accordingly so that it can be shown in the result after simulation. Then I added like another rule to iterate function, which simply ensures that water cell remains like a water cell. And finally, I had to define some boundaries for water bodies. Like in this case, you can see there are 4 vertical streams, which can be seen in the next slide when I run the simulation. So here we can see the adjustment we did in the previous slide. It actually shows that how the fire growth is restricted by the water. These 4 streams can be seen, and I think the fire is not spreading below them, but you can't see it clearly because there are these 4 streams I dropped. So yeah, I think this is an interesting result here. So we modified the original model by adding wind effect here, which dramatically affect the fire spread. So to achieve this, I modified the original neighborhood such that NY and NX respectively represent the first and second coordinate of the original neighborhood. And just below NX and NY, I had to define the NZ, which represent wind. So each value in NZ correspond to one of the coordinates in neighborhood NY and NX. Like if at least one of the index value in neighbor specifying pair of NY NX is negative, the corresponding NZ value in this case is 0.1. Otherwise NZ is 1. So as a concrete example, if you can see the first value of both NY and NX is -1, so this first pair of coordinates correspond to the neighbor at -1, -1 here. So thus the NZ value corresponding to this pair is 0.1. Actually this modification ends up like in biasing fire spread in direction that wind is blowing. In this final step, we had to modify the iterate function to check all neighboring cells. If a neighbor is on fire and randomly generated number is like less than the neighbor's NZ value, like 0.1 or 1, the cell catches on fire. So since the random number is a float which is greater than 0 and less than 1, when NZ is equal to 1, the random number will always be smaller and the cell will burn. Similarly, 0.1 is below most random numbers generated. So this biases fire spread with the wind direction actually, yes. And here you can see the results when we included wind in our experiment, and the NZ values are shown below here. So this is like quite interesting plot generated. And then I just try to play with some values to see if I increase the bias what will happen, and you see it's spreading more faster than the first plot, so than in the first plot. So yeah, I think that's all, the end of my slides. Thank you very much.